far side of our path around the sun lie our two closest planetary neighbors. Scientists theorize that 5 billion years ago, a vast solar nebula gave birth to Venus, Mars, and Earth, at the same time, from the same basic materials. We might well expect these planets to be Earth-like in many ways.
Venus is almost a precise twin planet of the Earth. It has almost the same radius, it has almost the same mass, and almost the same density. So it's of great interest to understand Venus as well as we can in order to compare it with the Earth.
Mars is a very deceptive planet. It's almost as though nature created something to mislead Earthbound scientists, because the length of the day is almost exactly the same as the Earth. Its tilt of its axis to its orbit, which governs its climatic variations, is very, very close.
When scientists finally sent probes to these worlds, they found there remarkable similarities and startling differences.
Even though Venus is one of the planets that was known to the ancients, observations of Venus have always been difficult for two reasons. One is that it's an inferior planet. That means that it's between the sun and the Earth at all times.
If we think about Mercury and Venus, they're on the inside lanes. They travel around the sun in orbits that are closer to the sun than the Earth is. And so they stay close to the sun in the sky. And about the only time we can see them is when they are relatively far from the sun, before dawn in the dawn sky, or after sunset in the evening sky.
One always has to observe Venus at near sunrise or near sunset, and hence you have to look through a tremendous amount of the Earth's atmosphere, which distorts the light coming through it, making resolution of surface features in the Venus atmosphere more difficult. The second problem is related to the Venus atmosphere, or the Venus clouds itself. One can never see the surface, one only sees the cloud tops. And the cloud tops had always appeared to Earth-based observers to be predominantly white or very highly reflective.
For many years, this thick white shroud prevented astronomers from determining the rotation rate of the planet itself.
Radar astronomy came on the scene. And what the radar astronomy folks were doing was bouncing radar waves off the surface of Venus. Radar astronomy grew in precision with every successive few years to show us that Venus rotates, or solid Venus rotates, once every 243 Earth days. In fact, it rotates slower than it orbits around the sun. Now, what's interesting about these radar waves is that Venus was rotating clockwise as seen from above, backwards from all the other planets.
The best guess we have as to why Venus is different is that Venus, like perhaps most of the terrestrial planets, suffered a major collision during its early history with an object of comparable size, and as a result of that collision, the spin or the rotation of Venus was changed from an initially prograde to its present retrograde state.
Venus's retrograde motion surprised planetary scientists, but various space missions to map and even land on the planet brought the most astonishing revelations of all.
Until recently, Venus was a veiled planet. The cloud layer hid many of its secrets from us. The Magellan program has now allowed us to peek beneath the veils of Venus, and for the first time to reveal the geology, the structure of the surface. And what we've been discovering shows us a fascinating world with its own set of volcanoes, its own set of unique features, and many, many surprises that will come out as we study the data.
Venus does not have anywhere near as extensive ups and downs as we have in the Earth's continents, but there are isolated marked features like the plateau called Ishtar, which includes a mountain 10 kilometers high near the North Pole. There have been found about 914 craters on Venus. This is a lot less than you'd find in the same amount of area on the moon, because a infalling body which is smaller than a few kilometers gets broken up by the Venus atmosphere, and so only the biggies get through.
Magellan also revealed strange bulges called arachnoids and corona, perhaps caused by hot currents of magma rising below the planet's crust.
One of the big questions when we first started exploring Mars and Venus and Mercury was, do those planets also have continental drift, that is plate tectonics, collision of plates, like make the Himalaya mountains and so forth? And a lot of speculation, especially when we only had Earth-based radar bouncing back and forth. But we know now that none of these planets have them.
It does appear that there might be something similar to plate tectonics in the case of Venus. There's mountains that are very high that are apparently being held up by compressional forces. There's rifts that look very similar to the rifts that we see at subduction zones and the continental margins in the western part of the Pacific Ocean. Although again, these are just they occur very locally. It's not a planet-wide phenomena.
Venus has some strange things happening on it. We don't really know all about it, but it's not plate tectonics in the way we have it on the Earth.
One reason it might not be more identical to the Earth is the plates never cool off very much. So they never get as dense or as cold as plates on the Earth's surface, and it might be hard to have them sink back into the interior. And even if they do, they might come right back up again. We do know that because the mass and the density are about the same, that the interior structure is probably very similar. Venus probably has a large core, approximately half the radius of the planet, and it's probably mostly iron in order to make the density of the planet come out right.
We see a planet that's the same size as the Earth. We know it has an interior that's hot because we see volcanism at its surface, so we know there's heat coming up from the interior, and yet when we search for a magnetic field, we find no magnetic field. What's going on at Venus?
Here's a planet that's very much like the Earth, and presumably its interior is like ours, and yet there's no dynamo in the interior of Venus that's capable of generating a global magnetic field. One of the speculations which has been advanced is that it's lacking a solid core at the center. There are reasons for believing that the other planets that have magnetic fields, like the Earth, have a solid core at the center surrounded by a fluid core.
We know all of these things for the Earth, and that's because we have a lot of seismic data that's relevant to the interior. So until we do get this kind of information, it's, I think, fairly safe to assume that the interior structure of Venus is very similar to the interior structure of the Earth, and that includes a large metallic iron core.
While our missions to Venus revealed a terrain and internal structures somewhat different from Earth's, they also discovered a forbidding environment unlike any other in our solar system.
Many people like to say that Venus is the sister planet of the Earth. But if it's our sister, it's certainly a twisted sister, not a sister of the kind that you want to show off at family gatherings. Venus's environment, because of what happened early on in its history, has truly become one of the most alien places in the solar system. From space, Venus looks surrounded by a tremendous fleecy cover of clouds, which you might find rather inviting if you didn't know any better.
Early astronomers and planetary scientists figured that since the atmosphere was full of clouds, that usually means that you have a lot of humidity and water vapor condensing to form the clouds. If you have humidity and water vapor, you have swamps, swampy surface. You have swamps, you have jungles, and if you have jungles, there must be dinosaurs and alligators living in the jungles. So from starting with the fact that you couldn't see anything on the surface of Venus, you reach the conclusion that there must be dinosaurs there. And the fact of the matter is that there are no swamps on Venus. The oceans boiled off the surface eons ago. The water vapor has somehow escaped to space, and it's a dry, it's a superheated planet that's completely uninhabitable.
The pressure is tremendously strong, like being deep underwater. And the atmosphere is made of more than 95% carbon dioxide. So your first deep breath would be your last deep breath. If you were to land on Venus, you'd have your choice of being crushed to death, asphyxiated, or French fried.
When we go to Venus, what we see are temperatures far higher than what would be expected for a body at that distance from the sun. In fact, temperatures on the surface of Venus are over 900 degrees Fahrenheit, which are enough to melt lead. And it was found out that this is caused by a runaway greenhouse effect in the atmosphere of Venus, where the carbon dioxide in the atmosphere, as well as other constituents like water vapor, are enough to trap incoming solar light.
It's like placing a blanket over yourself on a cold night in a cold room. If you, say, didn't have a blanket on, then your body heat would be radiated into the room and you get very cold. If you throw a blanket over yourself, of course what happens is your body heat is trapped by the blanket. The heat builds up under the blanket very quickly and it becomes comfortable in a fairly short time.
In the case of Venus, it's raised temperatures to these unbelievable levels, and we can therefore use Venus as a laboratory in the extreme to test the physics of the greenhouse effect as well as the models to see if they can predict what we see on Venus.
These models must also explain why the atmosphere of our sister planet evolved so much differently than our own.
Venus and the Earth are two objects of approximately the same size, formed approximately at the same time from approximately the same materials, and carbon dioxide is not an abundant gas in the Earth, so here's something that's a little counterintuitive and makes for an interesting challenge. Venus was just close enough to the sun such that water in the Venus atmosphere was driven off, and water never existed in a major way in liquid form on the surface.
There's a little bit of evidence that there might have been running water, but the main evidence that there might have been more water in the atmosphere and on the surface of Venus comes from isotopic evidence, in particular oxygen isotopes, which indicate that maybe 2 or 3 meters of water have been evaporated from the surface of Venus.
On the Earth, on the other hand, water did exist, and principally a liquid form. And that water as a liquid and as acids would enter into chemical reactions with terrestrial rocks and also with the carbon dioxide in the Earth's atmosphere, and it formed carbonate rocks. And the carbonate rocks precipitated on the floor of the oceans, and that's where they remain today.
It's buried in limestone sediments, and from what we understand about how limestone is laid down, this is carbon dioxide that was once in the Earth's atmosphere, but because of processes in the ocean, including shellfish making little shells out of calcium carbonate, that carbon dioxide is now buried on Earth.
The Earth and Venus started out with the same amount of carbon dioxide. Most of the carbon dioxide in the Earth's atmosphere ended up bound up in the rocks in the crust. That never happened on Venus, principally due to what water was able to do on one planet and what it was not able to do on the other.
The atmosphere of the Earth might be very different if the Earth were moved to the orbit of Venus, because then the oceans would boil away and we'd have a steam atmosphere, a water vapor atmosphere, and if it had always been that hot, then perhaps the carbon dioxide, which is present on Earth, would not have precipitated into the limestone sediments, but would still be in the atmosphere. And we might have a sort of carbon dioxide water vapor atmosphere instead of the oxygen, nitrogen atmosphere that we have.
While the Earth and Venus share the same beginnings, Venus evolved into a world with a less active geology and a hellish environment. Further from the Sun, our other planetary neighbor developed into an intriguing world of its own, more hospitable, yet largely unpredicted.
Mars is perhaps the most fascinating world in the solar system for us Earthlings, because probably it's the most Earth-like planet. you have to separate two versions of Mars, the mythic, what I call the mythic Mars, up till maybe the 1930s or so, and the real Mars that we discovered after that. And it's important to understand the mythic Mars.
It's close enough so that even with primitive telescopes, we began to be able to make out some detail on the surface of the red planet. For example, it was early on learned that Mars appears to have what looks for all the world like polar caps, regions of ice at the North and South Pole, leading many early astronomers to think that it might have water. It also appeared to have changes which went with the seasons, what we call seasonal variations, which implied that perhaps there was vegetation which changed its appearance as the planet went from summer to fall to winter to spring and back to summer again.
And the idea was that if you have these dark areas on Mars that change from summer to winter, they must be plants. You have evolution. You must have plant life evolve on Mars. Life must have evolved on Mars. So now the mythic Mars of 1880, let's say, was a planet with ice caps on the poles, with clouds, with dust blowing around, with big areas covered by forests or plants that got darker or maybe greener in the summertime, faded sometimes in the fall or in the winter, and sounds a lot like the Earth.
These views were ultimately shattered by the Mariner and later the Viking missions to Mars.
On July 15, 1965, Mariner 4 flew by Mars and became the first spacecraft ever to send back television pictures from another world. We got 22 pictures back from Mariner. Today, compared to the kinds of pictures we have from Viking and Voyager, these pictures seem extremely primitive. But in those days, they were called the pictures of the century. People could not believe that we were actually getting television pictures from the surface of another world. To those who were science fiction fans, the Mariner 4 images were a tremendous disappointment. No sign of life. Mars seemed a barren, desert-like world with craters, with not much evidence of anything interesting happening.
The southern hemisphere of Mars looks a little bit more like the Moon. It's rugged uplands with lots and lots and lots of ancient craters, so it's very ancient crust. It's been heavily cratered. It's broken by some big canyons, particularly this huge canyon called Valles Marineris, which was discovered by the Mariner space program.
This is so much bigger than any comparable canyon on the Earth. It makes the Grand Canyon seem like a little tributary somewhere. How that happened, we don't really know very well. Somehow the crust has pulled apart there, and either material is sunk down inside, or it's been transported elsewhere. It's very hard to see how it could be transported elsewhere, where it could have gone. So most ideas have it sinking down, and maybe somehow it's connected with the boiling up of lava in these adjacent huge volcanoes.
Because scientists found the southern hemisphere of Mars to be a world of ancient craters and valleys, they were surprised when probes over the northern hemisphere discovered a much younger, more active surface.
It has big mountains. It has some volcanic peaks with gentle slopes. These big volcanic mountains on Mars rise up to something like 3 times the height of the largest mountains on the Earth.
A Martian tourist would absolutely have to see the volcano called Mount Olympus. Mount Olympus is a towering mountain, and it's a volcano very similar to the kind of volcanoes we have on the Hawaiian Islands, what's called a shield volcano, but it is far larger. How did such an enormous volcano, much larger than anything we have on the Earth, form? The reason we believe is that Mars is a stillborn planet in some ways.
Remember, on the Earth we have continental drift. If you have a hot spot in the mantle bringing up lava, you have an eruption, you make a volcanic mountain. 10 million years later, that has been carried off the hot spot, and some new lava comes up, it piles up someplace else. In fact, the whole string of the Hawaiian Islands is a great example of that. There's one hot spot. You formed an island, it got pushed to the northwest, and you formed another island, it got carried to the northwest, you formed another island.
On Mars, which is smaller and colder, This process of shifting plates, which we call plate tectonics, never quite got started. It tried, but it never worked. And so it's a one-plate planet. And as a one-plate planet, if material is seeping up from a hot spot, it just seeps up and up and up and builds up enormous volcanoes.
When we look at Mars, we're looking at a medium planet. It's about halfway between the size of the moon and the size of the Earth, has a little bit of heat left inside, some of the heat has gotten out. We see big volcanoes on its surface. We also see craters and very old surface that has never been geologically active. So we see a medium planet. It's medium size and has a medium amount of heat inside it.
The density tells us that there's probably an iron core in Mars. We don't know how big it is, and we don't know what its composition is. For example, it could be a fairly small iron core, or it could be a fairly large core that's composed of iron plus sulfur or iron plus oxygen. And until we get seismic data from the interior of Mars, we really won't know.
From its cooler interior to its numerous craters and massive volcanoes, Mars has proven to be less Earth-like than we once predicted. Still, billions of years ago, these two planets may have had much more in common.
Now, Mars got more interesting in the early 1970s when we sent Mariner 9 there. First spacecraft to go into orbit around Mars and do mapping. And it discovered something very strange. There's no liquid water on the surface. It's frozen. It's a dry planet. But Mariner 9 discovered that all over Mars are what seem to be dry riverbeds.
There are channels on Mars, a wide system of channels, which seems to imply that early in the history of Mars, billions of years ago, there may well have been a very different kind of world there. A world with flowing water, a world with rivers and perhaps small lakes, a world with a much thicker atmosphere, a world which would make today's Mars look very, very dreary in comparison.
The most puzzling aspect of the features on Mars has been the so-called channels, especially those that look clearly like they're formed by giant floods. These are much larger floods than anything that now happens on the Earth. The only analogy are floods that happened at the end of the last ice age. I mean big. We think something like that probably happened in an early phase on Mars 3 billion years ago.
So this water either disappeared off the planet or disappeared into the interior of the planet, but it is certainly not on the surface today. And in fact, you can explain most of the features on Mars with a very small fraction of the water that exists on the Earth.
Billions of years ago, as the planet cooled, some of this water may have been frozen in the legendary polar caps of Mars.
In the winter, carbon dioxide frost, like dry ice, what we call dry ice, condenses out of the atmosphere, forms a very broad polar cap, and in the summer it shrinks way back, all the carbon dioxide disappears, and you have a little white polar cap, which is water ice. And it never gets warm enough to really melt that frozen water on the pole of Mars. So there's a reservoir of water at each pole, but it's frozen.
Around the polar caps on Mars, on both the north and south, are smooth banded deposits with little terraces on them that go for, again, thousands of miles. They're huge. We realize that these must be formed basically by dust falling in. These are air-formed deposits. They're not water-formed deposits. But that requires enormous dust storms. It requires ice or something sticking it together.
Indeed, global dust storms regularly repaint the surface of Mars, yet its atmosphere is much less dense than that of other planets.
The atmosphere of Mars compared to the Earth is very different than Venus compared to the Earth, whereas the surface pressure on Venus is 100 times greater than Earth surface pressure. The surface pressure on Mars is 1/100th the surface pressure on Earth. And so we have a very thin atmosphere composed mostly of carbon dioxide.
How did those atmospheres get to be so different? The answer seems to be that Venus is more massive, and so it's outgassed more carbon dioxide from its interior and built a bigger and thicker atmosphere, and because it's hotter, it doesn't have oceans to dissolve the carbon dioxide out of the atmosphere. Mars is smaller and has less gravity, and so it has lost some of its atmosphere. Small planets just can't hold on to their atmosphere as well as large planets.
But on the other hand, Mars is a little farther away from the sun, so it's a little cooler, so the atmospheric gases don't move around as much. So that's a competing set of relationships. One, Mars is a little cool, so the gases tend to stay around. On the other hand, it's not quite as massive, and the gases tend to get away. In Mars's case, most of the gases got away, and we don't observe large amounts of oxygen in the atmosphere of Mars either. Earth is the one standout in that regard.
So, the exploration of our closest planetary neighbors has revealed two worlds that evolved along radically different paths, despite their early similarities with Earth.
The Earth is one member of a family of worlds, each with their own personality. And so the idea then is that while the physics operating in all of these worlds is identical, because of the personality of these worlds, namely their mass, their initial position from the sun, the tilt of the axis, the rotation, the physics therefore manifests itself in dramatically different ways. And it gives us a better understanding, therefore, of that physics, which, when looking back to Earth, gives us a better understanding of the physics driving Earth phenomenon.